It's important to know the difference between an amine and an amide. In an amide, the nitrogen is bonded to the carbonyl carbon. The nitrogen in the amine is not. Amines are basic, but amides are not. To name amides, you replace the ic acid from the carboxylic acid with amide. Okay, so just to give you an example here, we have, okay, this is a primary amide, and the carboxylic acid was acetic acid. So we are going to take the ic acid and we're going to replace it with ATE. No, not ATE, sorry, amide. So it's going to be acetamide. Okay. Then, if there are alkyl substituents on the nitrogen, you name them first and write an italicized N before the alkyl name to show it is attached directly to the nitrogen. Let's do an example of that one. Okay, so this is benzoic acid right here. And we're going to attach a couple alkyl groups. And this is going to be a tertiary amide. Okay, so we want to start with naming those alkyl groups. So we have an ethyl and a methyl, so we know we need to start with the ethyl first. And to show that it's attached to the nitrogen, we use an N. Say N-ethyl. And then we're going to do that again with the methyl. And then we're going to name the carboxylic acid, which again I told you was benzoic acid. And so we're going to take off the ic acid and put amide. So methyl benzamide. Okay. This is just an overview of what we've already mentioned about carboxylic acids, esters, and amides. It says all undergo carbonyl group substitution reactions, and we're going to look at that a little closer. Esters and amides are made from carboxylic acids, right? We take off the OH from the carboxylic acid and add an alcohol. We'll form an ester, and again, we're going to look at these reactions. The amide forms by taking the OH off the carboxylic acid and adding an amine to it. It says esters and amides can be converted back to the carboxylic acid, so these reactions are reversible. Carboxylic acids and unsubstituted or monosubstituted amides exhibit strong hydrogen bonding to one another, so that's the primary and secondary amides. Disubstituted amides and esters do not hydrogen bond to one another because there is not that hydrogen available to do that. Simple acids and esters are liquids. All unsubstituted amides, except for formamide, are solids. Carboxylic acids give acidic aqueous solutions. Esters and amides are neither acids or bases. Small amides are water-soluble, while small esters are somewhat water-soluble. And volatile acids have strong, sharp odors. Volatile esters have pleasant, fruity odors. And amides are generally odorless. So again, that's just kind of a overview of what we've already mentioned. Acetic acid, or is the common name. The IUPAC name is ethanoic acid, is the primary component of vinegar with a concentration of 50% acetic acid. It becomes corrosive and can damage skin, eyes, nose, and mouth. But with vinegar, usually you have about a 4 to 8% solution of acetic acid. And then pure acetic acid is called glacial acetic acid because as you cool it, the liquid forms icy looking crystals that resemble glaciers, so we call it glacial acetic acid. Citric acid is a tricarboxylic acid. Just to show you this, you don't have to memorize this or anything. So citric acid looks like this. Sorry, I'm running out of room here and writing the wrong thing. So we have 3 carboxylic acids all together here. So that's what makes it a tricarboxylic acid. So again, you don't need to know the structure or anything. I just wanted to show you what it looked like. So that's citric acid. It contains 3 carboxyl functional groups. It is produced by almost all plants and animals during metabolism. Lemon juice contains about 4 to 8%, and orange juice is about 1% citric acid. Pure citric acid is a white solid, and it's very soluble in water because, I just showed you that the structure, and it has, 4 OH groups on there, able to, have hydrogen bonding. Citrates are used to buffer pH. Carboxylic acids establish equilibria in aqueous solution with carboxylate ions, and I kind of mentioned that at the very beginning of chapter 6. But just to give you an idea here what that looks like. Okay, so here we have acetic acid. Maybe. There we go. Okay, put it into the water. And again, it'll establish an equilibria because the hydrogen is going to come off. And so we're going to get a negative ion, and the water is going to accept that hydrogen. And so we get a positive there. So this is the carboxylate ion. So to name the carboxylate ion, all we did was we took the IC off of carboxylic and we replaced it with ATE, so it becomes carboxylate. To name that anion, so you can do that with any of the, that's what any of the carboxylic acids do. And at physiological pH, carboxylic acids mainly exist as their carboxylate ion. The strength of an acid is measured by its acid dissociation constant. The smaller the Ka value, the weaker the acid. Your book also talks about the pKa value, and actually that's the opposite. The higher the pKa value, the weaker the acid. So there's both in table 2 on page 199, and for the Ka values that are shown, it's going from a higher number to a lower number, and that shows, stronger acids have the higher number, weaker acids have the lower number. Trichloroacetic acid is the strongest of the acids because it has that higher Ka value. And then glutaric acid is the weakest. It has the smaller Ka value. And when carboxylic acids undergo a neutralization reaction, so that's, it's an acid when it's reacted with a base, then water is produced and a carboxylic acid salt is produced as well. So if you remember neutralization reactions, we always have water and a salt. That is the same thing here, except we have water and a carboxylic acid salt produced. So just to show you, again, we have acetic acid. So that's our acid, and here's our base, NaOH. So the hydrogens, or the hydrogen here, and the hydroxide, so hydrogen and hydroxide are going to come together and produce water. And then we're going to get the carboxylic acid salt. And we have a negative ion there,